right, lesson 14, modeling relationships with a line. This is where we're going to use our calculators. It'll be in the lesson though. It's spelled out, so you might want to get your graphing calculator ready so you can practice along with us. First of all, example 1. Kendra likes to watch crime scene investigation shows on the television. She watched a show where investigators used a shoe print to help identify a suspect in a case. She questioned how possible it is to predict someone's height from his shoe print. To investigate, she collected data on the shoe length in inches and height in inches of 10 adult men. Her data appeared in the table and scatter plot below. So we have shoe length. That is in inches and the height of the people. And then they plotted the shoe length in inches and the height. So, for instance, this is a decent length. I've got a height of 68. That would be in inches also. We go up here, super tall, pretty big foot, but foot got bigger, person got smaller, whatever. All right, we're going to ignore that linear equation there in the corner for a little bit. All right, let's look at exercises 1 and 2. So exercise 1, it says, is there a relationship between shoe length and height? It looks like it. Oops. If you look at the data, it looks like I can fit a line in there somehow. Excuse me. How would you describe the relationship? Do the men with longer shoe lengths tend to be taller? It seems that as the shoe length increases, the men do tend to get taller. We did show, or I highlighted a few at the end where we had pretty long shoe length, the tall guy, and then a shoe length that got longer, and the guy didn't get taller, got shorter. But overall, it looks as though as the length increases, the men do tend to get taller. Okay, looking at example 2, when two variables x and y are linearly related, you can use a line to describe their relationship. It's our model. You can also use the equation of the line to predict the value of the y variable based on the value of the x variable. We did this in lesson 13 a few times. For example, the line y equals 25.3 plus 3.66x may be used to describe the relationship between shoe length and height, where x represents the shoe length and y represents the height. And if you look at the graph of that, x would be your x-axis would be your shoe length, and your y-axis would be your height. To predict the height of a man with a shoe length of 12 inches, you should substitute 12 in for the x equation of the line, and then calculate the value of y. That's where you substitute 12 in right there for x. You would use that model, that linear equation, to predict a height of 69.22 inches for the man with a shoe length of 12 inches. Okay, that's how it works. All right, below is a scatter plot of the data with 2 linear models. So it's the data you already saw. We've got 2 linear models here. Y equals 130 minus 5x. Here we have a negative slope and a y-intercept of 130, so that would be this line, because if this continues all the way up, it would cross the y-axis at 130, and my slope is negative. Okay, and the other one is y equals 25.3 plus 3.66x. Here's my slope, there's my y-intercept, my slope is positive. My y-intercept would go down until it would reach about 25. Okay, doesn't look like we're quite with our y-intercepts there, but you get the idea. Which of these 2 models does a better job of describing how shoe length x and height y are related? Explain your choice. I would say that equation right there does a better choice, because as shoe length increases, the height of the person also increases, which is a positive slope. Right, one of the men in the sample has a shoe length of 11.8 inches and a height of 71 inches. Circle the point in the scatter plot in exercise 3 that represents this man. I went ahead and copied that plot over so that we could see it. And if we look, that would be that man. Okay, 11.8 and 71 inches. All right, suppose you do not know this man's height, but you do know that his shoe length is 11.8. That's an 8 right there, 11.8. If you use the model y equals 25.3 plus 3.66x, what would you predict his height to be? So let's use y equals 25.3 plus 3.66 times 11.8, and we would get a y value of 68.488 using my handy dandy calculator. That would be in inches. And if we use the other model, 130 minus 5x, except for x, I need 11.8. I would get a value of 71 inches. So using the first model, the man's predicted height, because remember we're using the model, so it's a predicted height, is 68.488, and then the second model, his predicted height is 71 inches. Which model is closer to the actual height of 71 inches? That would be the second. Is that model a better fit for the data? Explain your answer. So the model was closer to the actual value, but it's not the better model because the first model is closer to more points. Is there a better way to decide which of two lines provides a better description of a relationship rather than just comparing the predicted values to the actual values for one data point in the sample? The better line is called the line with the best fit. So the better line is the one where the distances from the points to the line, which is the model, is shorter. So the distances from the points to the line, which is the model, are shorter. That is the line with the best fit. So as you look at your graph and you have your points and then you have your line, we would actually measure the distance from the point to the line, and the line that has the smallest total distance is actually the line of best fit. These are called residuals. All of those blue distances are the residuals. You want the smallest total residual to get your line of best fit. So let's look at the residuals. One way to think about how useful a line is for describing a relationship between two variables is to use the line to predict the y values for the points in the scatter plot. These predicted values could then be compared to the actual values. The predicted values are the ones on the line. I don't know why I said one. On the line are the predicted values. compared to the actual values, which are the points. For example, the first data point in the table represents a man with a shoe length of 12.6 inches and a height of 74 inches. If you use the model or the line to predict this man's height, you would get 71.42. So predicted using the model is 71.42. His actual is 74. You calculate the prediction error by subtracting the predicted value from the actual value. It's called the residual. Okay? The first data point, the residual is calculated as follows, 2.58. So if you look at this, for the line y equals 25.3 plus 3.66x, calculate the missing values and add them to complete the table. So let's do the predicted. We're going to plug in the shoe length into x and calculate the predicted y value. You would need a calculator for this. So I'm going to go ahead and calculate these. I'm just substituting x into the equation and calculating. And then I'm going to go ahead and take the actual height minus the predicted height and get the residual. So 65 minus 48.49 is given. 71 minus 69.95. 68 minus 67.02, 69 minus 69.95 given. That's it, table's full. So number 9, why is the residual in the table's first row positive and the second row is negative? If the actual value is larger than the predicted value, the difference is positive. If the actual value is smaller than the predicted value, the difference is negative. What is the sum of the residuals? So you take the residual column and you add it all together. So adding all that together, I get negative 0.6. That's actually really close to 0. Because the positive and negative values of the residuals balance each other out. Okay, not all the residuals are close to 0, but the positives and the negatives balance each other out. When you use a line to describe a relationship between two numerical values, the best line is the line that makes the residuals as small as possible overall. Okay, you want that total residual as small as possible. If the residuals tend to be small, what does that say about the fit of the line to the data? Smaller residuals, smaller residuals are a good thing. It's a good fit. The line is pretty awesome. The most common choice for the best line is the line that makes the sum of the squared residuals as small as possible. So squared residuals makes everything positive. Okay, if I square all the residuals, it makes everything positive. And then if I add them all together, the smallest square fit, the smallest sum of the squared residuals is the best. So let's go ahead and add a column to the right of the table in exercise 8. We're going to skip this for now and we'll come right back to it. And calculate the square of each residual. And I'm just going to say it's r squared. I'm just going to square each one of those residuals. First one, I'm not going to write everything down. We can just look at it. And you can add that into your work. Okay, I'm going to push pause and finish. Okay, there we go. That's this r squared values, and we put them in there. I can't erase it, but I'm actually going to work on number 12 now. If we can go ahead and read that through my scribbles. Why do we use the sum of the squared residuals instead of just the sum of the residuals? When I square them, if I have a negative number and I square it, it becomes a positive number. So I'm squaring all of the residuals to ensure that they're all positive, so that when I add them together, I get an actual sum. I can actually see how well my data fits. So if I add all the positive numbers together, I get an actual sum, and if my r squared value is small, I have a good fit. Previously, when we had positives and negatives, we don't necessarily know if we're a good fit because the positives and negatives will balance each other out. We still have a pretty good fit when we have a small residual, but the r squared values give us a better idea of whether it's a good fit or not. So, to summarize, if you add all the residuals, positives and negatives can offset each other, and you get a small sum, even if some of the residuals are really big. If we square them first, that gives us all positive values, and it still reflects how far the data is from the line, so it's pretty cool. If I add all of these together, let me get a different color. If I add all of these residuals together, I get 34.54. Okay, it's a much bigger number than the negative 0.6 we had previously when we summed all of the residuals together. All right, the least squares line, the best fit line. Here's where you need your calculators. The line that has a smaller sum of squared residuals for this data set than any other line is called the least squares line. This line can be also called the best fit line, or the line of best fit, or the regression line. Okay, these are all terms that I use all the time. I'll usually call it the line of best fit, but they can be called all of these. For the shoe length and height data for sample 10 men, the line y equals 25.3 plus 3.66x is the least squares line. No other line would have a smaller sum of squared residuals for this data than this line. There are equations that can be used to calculate the value for the slope and the intercept of the least squares line, but these formulas require a lot of tedious calculations. Fortunately, a graphing calculator can be used to find the equation of the least squares line. I'm going to show you how to do that, but I think I copied in here how to do it too. If not, I'll copy it in real quick. Okay, I'll print this out for you guys so you can have it handy. But this is how you find the regression line, or the least squares line, or the line of best fit, any of those things. It's using that stat menu. We've already learned how to put things into your lists with the stat menu and the edit option, and then linear regression. Oops, sorry about that. We're going to do the linear regression option. Okay. And what else do I want to tell you on this page? All right, so yeah, we'll do this tomorrow in class. All right, exercises 14 through 17. Enter the shoe length data and the height data and use your calculator to find the equation of the least squares line. Did you get y equals 25.3? Again, we're going to do this tomorrow to practice, but when I did it, I got 25.2768959. how many other? 50413 plus 3.6570247933884x. Lots of digits, which we obviously don't need. So when you round all that, yes, that is what you get. Assuming that the 10 men in the sample are representative of adult men in general, what height would you predict a man whose shoe length is 12.5 inches? We're going to use, if we had our calculator, we could do this a lot easier because we have that line of best fit in our calculator now. But plug and chug right there, I get 71.05 inches. That's the predicted, yep. And then 11.9, oops, would give me, let's calculate, 68.86 inches. Cool. Once you found the equation of the least squares line, the value of the slope and the y-intercept of the line often reveals something interesting about the relationship you are modeling. The slope is always the number in front of the x, and the y-intercept is the constant by itself. The slope of the least squares line is the change in the predicted value of the y variable associated with an increase of 1 in the value of the x variable. So the slope, if you increase 1 in the value of the x variable, your slope is the change in predicted value of the y variable. So given an interpretation of the slope of the least squares line, that means for every 1 inch of shoe length increase, a person or man is 3.66 inches taller. So for every 1 inch larger of shoe length, the person is 3.66 taller in height. The y-intercept of a line is the predicted y value when x equals 0. When using a line as a model for the relationship between two numerical values, it often does not make sense to interpret the y-intercept because a 0, x value of 0 may not make any sense. That would be their shoe length of 0. That means that they would be 25 inches tall, which doesn't make sense, right? 0 shoe length and 25 inches tall. That's why it just doesn't make sense. So the y-intercept is not a very valid number. Cool, that's it. Long lesson, sorry, but very important. So we're going to do the calculator thing tomorrow.